Good afternoon, everyone, in person and online. I would like to start by acknowledging the traditional owners of our land in which this seminar celebrates today and paying my respects. Today we have the pleasure to have with us Xinjiang Xuan, who is an assistant professor at Hong Kong Polytechnic University, and he received his PhD from the Imperial College London. And before he moved to Hong Kong, Dr. Xuan was a postdoc at the UC Berkeley in California, where he conducted research with NASA on spacecraft fire safety. So he's also an associate editor of the International Journal of Wildlife Fire and Fire Technology, and an editorial member of the Fire Safety Journal, a board member of the International Association of Wildlife Fire, and a committee member of the UK Fire Safety Code. He has received a long list of awards, so well done. I'm not going to read them all. But yes, we are very happy to have him here, and I hope you all enjoy his seminar. I give the word to you. Thank you.
Thank you. Thank you for the introduction. Thank you for the invitation. It's actually a big theater here. Haven't been teaching face-to-face for like 2 years, so it's good to come to the classroom eventually. So the topic today I'd like to talk is about smoldering fire in Peatland, and from the scale point of view, it's probably the largest fire on Earth. And I have been working on this topic since my PhD, so it's almost like 10 years. And for the work today, most of the work is done actually by my first PhD student, Dr. Shaoren, and Yun Zhu. He's a new PhD in my group, and my supervisor, Guillermo. So this kind of collaborative work. So I have to say some background about myself and my current research is I'm an engineer, trained engineer. So I know this is like a natural science forestry department. So some of my method may not be very common to you guys. And most of my work is related to the building fire, structure fire, small fire fighting. So the wildland fire is just part of my research. Okay. So today I'd like to share something. Mainly about a few parts. First, I'd like to say something about this peat fire. Many people are not very familiar with this kind of disaster. Actually happen everywhere in the world. And then I'll talk about the dynamics. How do we conduct some experiment to explore these fire dynamics in the lab? And then I'll try to say something, how can we, using engineering method, to scale up the lab experiment to study the Earth scale phenomenon, and some challenges, frontiers I mentioned in the end of the talk. So let me start with a video for those who have not seen the peat fire before. So this is a typical peat fire. That's I think 2015 in Indonesia, and you can see the whole forest is burning, but you cannot see a flame. So you see the smoke everywhere. Basically, what's burning is the soil, is a peat soil on the ground. And these soil, they burn flameless. So you cannot see the flame, but they are burning there. It's like burning cigarette and generates so much smoke. So it's probably, I think in terms of scale, in terms of the time it lasts, it probably is the largest and long-lasting combustion phenomenon on Earth. Okay, so for such a large fire, if you look at that from, let's say, Earth scale, so this is a satellite image during that 2015 fire. So all the red spot here is the peat fire captured in the satellite in Indonesia, and we have Malaysia here, we have Singapore here. So I don't know if you have visited Singapore in the summer. If you go there, often a few weeks will be like completely covered by haze, the whole Singapore city. And I'm from a country whose is full of haze event as well. So Now it's maybe getting better. So if you go to Beijing, you will see very heavy haze. So they are both haze event. And of course, the fundamental reason is different. But if you look a little bit deeper, so most of these haze, they are coming from incomplete combustion. So for the forest fire, for the peat fire, it's incomplete combustion in smoldering, but in the city, like in Beijing, it's like engine car, and the power plant's not burning like cleanly. So basically, these haze come from this incomplete combustion. So this is another lamped satellite image for the peat fire in 1997. So that's probably the largest peat fire we have ever seen. And this satellite image shows the smoke propagation. You can see the scale of this propagation. So it's not just covering the Southeast Asia. Some even go to Australia, some go to Africa. So it's really a global event. And more importantly, it's a purely carbon source. So for such a single fire, it generated about 13 to 40% human-made carbon emission that year. So that's significant carbon emission. So let's look at the peatland distribution. So there are many peatlands all around the world, but mostly they are distributed either in the boreal Arctic region or in the tropical region. And I noticed that there's also some in Australia, and I have talked to some professors in Tasmania. They said they have peat fire there every year, so it's quite common. So although the peatland is only covering, let's say, 3% of the global surface, but it's actually store about 1/3 of the global soil carbon. So the carbon stay inside of the peat soil is about the same amount of the carbon stay in the atmosphere. So that's the scale we're talking about. And they're very, very vulnerable to the fire. And here are some pictures. Actually, this Australia one is I found yesterday from the internet. So it's from Carabula Lake. So it's like west coast of Australia. So they also have the peat fire there. And many other places, we have very massive peat fire. And if we look at the recent peat fire, we just highlighted these big ones over the last 20 years. So most of them are Northern Europe, Russia, Canada, Alaska, and most are here in Indonesia, including those in 2017, 2019, 1997, and 2015. So there is a clear connection between the El Nino effect with this peat fire. So we have very strong El Nino effect in 1997 and also 2015. That's the reason we actually have these two big peat fire around Southeast Asia. I think this year is also have very strong peak for the El Nino events. So there may be big fires coming in Indonesia or Malaysia as well. So we also, there's not really much thing we can do for such large scale fire. People, of course, try to fight this fire with human hands, with machines, but I have to say it's impossible. It's essentially impossible. And I have a little video showing some forest service from Germany. They're trying to control the fire, build some fire break. So you can see the fire is burning beneath it. If you just remove the soil above it, you can see the smoke. But if you don't remove the soil, you cannot see the fire below it. In fact, once you remove the soil, it gets more oxygen, so fire becomes even stronger. So it's essentially very hard to control these fires. And more recently, we just realized that there are a peat fire even in the Arctic region. So this is like in Siberia, it's like minus 40 degrees Celsius. And we can see the fire still burning below the snow. So crazy. This is a very persistent combustion you can find. So that's a brief introduction about the peat fire phenomenon. So as an engineer, we're trying to understand this phenomenon, but of course we cannot just go out to bare forest. The best thing we can do is just collect some samples and do some experiment in the lab and try to find out how it actually burns, what's the combustion limit. So first thing, we have to understand the difference between the regular flaming fire and the smoldering fire. The regular flaming fires like candle flame, like forest fire. And the smoldering fire, the most common one is a cigarette, and the charcoal when you play with a barbecue. And they are very different. For the flaming fire, the temperature is very high. In general, it will burn relatively clean. But for the smoldering fire, it generates so much smoke because the combustion is not very clean. The temperature is relatively low, like 600 degrees Celsius. So it's not strong enough to generate a bright flame. And it's very slow, easy to ignite, difficult to suppress. So these are typical. I think you all have seen, like, some people put a cigarette into a trash can and it looks extinguished, but after a few hours, it starts again. So this is a typical smoldering fire. And we start with chemistry. So to understand all the phenomena. So smoldering is combustion. So all the combustion can be explained by a single step oxidation reactions. But clearly that's not enough. If we look at what comes from this peat fire, you can see the black char generated, and also you can see some white ash generated. So it means at least we need like 2 straight steps reactions, including the drying and also the pyrolysis gas to generate these black chars. And these black chars can be further oxidized into white ash. So that's probably the simplest explanation for the smoldering fire. Of course, you can add more reactions to fit the data, but fundamentally you have pyrolysis, you have oxidation, and oxidation is actually quite complicated. So that's the chemistry. I'm not a chemist, but that should be enough as an engineering model. And for any of the combustion phenomena, we have to look at the basic fire triangle. So to have a fire, to have a combustion, you need a fuel, oxygen, and heat. So that's a 3 element for every combustion phenomena. And here, the peat is a fuel. So the controlling factor becomes the oxygen supply and heat loss. So the significant thing about the peat fire is we care a lot about the depth of burn. So if you look at this diagram, you can see the roots are completely exposed. So all the soils are consumed in the fire. So if you have like a regular surface fire, like crown fires, the tree probably will survive. But if you just remove all the soils, the roots are dead. So these trees are completely dead. There's no way they can survive. And another important factor we want to know is the limiting moisture content. So we know how much water we need to suppress the fire. That's typical things. So in terms of the ignition, actually there are some classical experiments did by Dr. Franzen from Canadian Forest Fire Service. So he found there is a compensation factor between the soil moisture content and the soil inorganic content. So if the soil is very wet, very inorganic, it's difficult to ignite. So we actually build a computational model to simulate this process. And by doing that, we can see if you want a fire propagation, you will have 3 fronts: the drying front, pyrolysis front, and the oxidation front. And you change the moisture until the fire can no longer propagate. So basically, we build a model to explain all the data from the literature. So right now, if you just give me a sample, just tell me the moisture content, tell me the organic content, I put in the model, I can predict whether the fire can be sustained in this soil or not. But the general rule is, if you want to ignite a peat, you have to reduce the moisture to about 50 to 150% in dry mass. In terms of the peat fire spread, that's even more interesting. So this is a photo took by my friend, Brett, Nuria Brett. So you can see they follow very strict pattern. They don't burn everything. So why is that? We still don't know. So, but one thing we know is the fire like to stay near the roots. So this is the infrared camera. So you can see they actually burns very strong near the roots. The reason is the soil near the tree actually become drier because the roots actually dry these wet soil. So actually the fire like to follow these trees, to kill these trees. So that's a very something we didn't expect. And to study this peat fire, we actually do some experiment in the lab. So we just put peat in the box and we burn it. So I'll give you some examples. So this is a top view. So of course the video is accelerated like 660 times. So you can see the top is the dry peat, the bottom is wet peat. So if you're increasing the moisture content, the fire spread will become much slower. And one thing more interesting, if you look at this video, so you can see actually the soil will collapse. They don't really burn on the surface. They actually collapse and burn. So this is actually something the firefighters found in the forest, in the peatland. So they generated, it's called overhang structure. So the fire tend to stay below the surface. They don't burn on the surface. So sometimes the firefighters just get there, they actually put their foot there and collapse. Everything collapses. They trap there. So this is a very interesting thing we found. And the major reason is actually the heat loss on the surface is quite high. So the fire tend to like hide beneath the surface to burn. The other thing is we tested is called quenching effect. So if the soil is very thin, eventually the fire cannot propagate. So I'll give you some example. So if the soil thickness is only like 5 centimeters, then the fire can, initially they can propagate, but after a while, eventually they will put out. So we did some experiment, also simulations to prove that concept. And using this concept, we designed the fire break, try to help people to design a fire break. So if you dig out some peat, and how much peat do you need to remain on the soil to prevent the fire spread? So you don't have to remove all the peat. So we just did some example. So for example, this one, we have like a thicker layer peat remains. Here we have like 5 centimeter peat layer remain. So if you take a look at it, if as long as you keep the peat layer very thin, eventually the fire cannot propagate through it. So because in reality, in practice, you're trying to have a fire break, but you don't know if you remove the peat completely. So this is actually give you some principle. So our idea is you can keep 5 to 10 centimeter peat layer in that fire break. The fire still won't propagate. So you don't have to remove everything completely. So actually that's very interesting work. It's also featured in the cover in the International Journal of Wildfire. And some other things I did when I was doing my PhD is the in-depth peat fire spread. That's something, I'll show you the video. You know how crazy these kind of fires. So I put like a box of peat and I put some igniter on the bottom. And I can tell you, if you look at the top, right now the fire is already burning, but you can see nothing. No smoke, temperature sensor says nothing. So it's like 5 hours. After like 5 hours, the fire propagates up to the surface, they interact with the oxygen, release a lot of smoke, then they propagate downward. So that's why it's so hard to stop the peat fire, because you don't even know where it is. If it's like 5 centimeter, 10 centimeter below your foot, you still don't know where it is. That's the hard part. So the fire actually can hide beneath the surface, and they wait a few days to come out. And this is the peat fire. So we always have a theory about these underground peat fire. So there is a possibility these fire never stopped. So maybe last year there is a fire, the peat fire, we stopped the fire on the surface. There are still some spots below the ground. Next year in the dry season, these fire come back. So we may never stop these fire. So they just hide. So to prove that, so of course I want to do some experiment in the field. In Hong Kong, there's no such peatland. So we just build like 1 meter tall of these big columns, and we see if these fire can hide how deep it can hide. And the result is also a surprise to us as well. So I show you this is a temperature measurement of that fire. See how long it lasts. So the time is here. So this is like 1 day. The temperature is not that high. It's like 300, 200 degrees Celsius. Of course, but our thermocouple may not measure in the right place. So these fires probably just stay beneath the surface for weeks, months even. And we just have a small column. If the column is much larger, then it may stay longer. Initially, we thought this is extinguished, but it's still burning, still burning. For 7 days, 8 days. So eventually it's like this. So after 10 days, it stopped. It's just for such a column. And most of the mass still remain. And so right now we are building even larger to see how long it can. Maybe it will like last for months, something like that. So that's some dynamics we explored about feedback. And the challenging part about this laboratory experiment, of course, it helps we understand this phenomenon. We still need to scale up to understand the larger scales, the Earth scale phenomenon. So that's something I try to do over the last few years. For this peat fire, if we look at the scale, it has Earth scale. If we zoom in a little bit, we have like mega scale. If we further zoom in, we have like larger scale. Zoom in, we have small scale. If we took some samples, we can do some chemistry analysis. So you can do these studies at different scales. Okay, so maybe for each of these smaller scale, it could be a small mesh in that larger scale. So that's the idea. But in reality, it will be more complicated. So for experiment point of view, we can only do like micro scale, small scale, and large scale. And larger scale, I think there's only 1 or 2 experiments in the world because it's so easy to auto control. And for the mega scale, Earth scale, we cannot do experiment. We can do some measurements. So that's a principle. So if we look at the number of tests, we will notice that if you increasing the scale, the number of tests will dramatically decrease. If you increasing scale to do the test, the cost and the complexity will increase dramatically. So what we feel is the small scale is the best balance. So you can do it in the lab. You have some of the complexity and time scale and space scale is also reasonable for some understanding. So that's the starting point. We do small scale test and we're trying to explain in the even larger scale, in the Earth scale. So the first experiment we're trying to do is we want to understand whether the rain can stop the fire, or how big the rain, how long it rains can stop this fire, because we cannot rely on firefighters. It's impossible for human beings to stop these fires. We can only rely on the nature. So to understand that, we actually designed a very small scale experiment. Is we using the sprinkler head, so it's in the building, to generate artificial rains, artificial rainfalls, and we do that in the lab and trying to find out how long the rain and how big the rain needed to stop the fire. So I can show you some experiment. So this is an experiment we did. So we have a sprinkler on the top to generate these rainfalls, and we place these fire at different location. So this is a sample we burn. So we ignite it and we put at different locations because at different locations the rainfall intensity is different. So we control the time, see how long it can stop the fire. So this is the result we get. So we found that there is like a minimum rainfall. So if the rain is smaller than 4 millimeters per hour, so no matter how long you rain, it won't stop the fire. And the best way is you have heavy rain. So if you have heavy rain, of course you can stop it in a very short time. But there is also another limit. Yes, you at least need a 3 millimeter rain no matter how strong you are, you need that amount of water to stop that fire. So that's the limit we found from this experiment. We think it's a very useful. So you can, using this plot in the real application, if you have a rain, how long, and you can estimate the probability of the survival rate of these peat fire. The other thing we are trying to understand is this Arctic fire. So that's become a very hot topic. That's become very hot topic. Okay. So, okay. Yes. Not sure who's talking. Anyway, so we're trying to understand these the fire in the very cold weather. And what we do is we also do the small scale test. Is we actually basically just bought a freezer from this market, and we put the peat into these peat fire into these reactors and put the reactor into our freezer, so we can control the environmental temperature and see under what condition it can be ignited and it can sustain to burn fire. So this is the limiting condition we found is the temperature of the environment and the moisture content of the peat. So if you increasing the moisture content, it will be more difficult to having fire. But if you peat is very dry, you can have fire even below like -40 degrees Celsius. So with this flammability map, we can estimate how much of these this Arctic soil will be burned. So for example, in 2015, we will have, let's say, about 15 centimeters of the fire is burned, peat will be burned. If we have the global warming rate under the current rate is 0.44 degree per decade, then by 2050, we will have like 25 centimeters of the soil will be burned. By the end of this century, we will have almost 60 centimeters of the soil will be burned. So with this estimation, we can predict how much of the carbon can be emitted from this Arctic fire. So under the different global warming rate. So currently we are here, 0.44 degree per decade. And this is a warming rate for the Arctic region. Arctic region is always warming faster than the global average. And the result we found is actually eventually about 3% of the human burning fossil fuel equivalent amount can be released from the Arctic peat fire. So that's like significant amount will contribute to the global warming. Okay. So why this peat carbon emission is so important? Because the amount of the peat we have in the soil is very, very close to the atmosphere carbon, as well as all the living plants. Yeah, because the peat is about 1/3 of the whole soil. If you just release a little bit, just a little bit, it could be very similar to what human release from the Asian carbons. So the problem is this soil, it takes like 1,000 years to generate. So unlike the trees, if you have a tree, okay, it regrow after a few years, maybe a decade. But for these soils, it takes like thousands of years. So they are not renewable, let's say. So if you release the carbon, it will increase the temperature, makes the soil dry, makes the soil warm, and it will make the ignition probability even higher. So it actually generates a positive loop to keep increasing these peat fire all around the world. So that's the issue. Compared to other wildfire, flaming fire, it's not a big issue because most of the tree will regenerate in a decade. So the other thing we look into is about the ancient oxygen cycle. So one question I ask my students all the time is, why it's like 21% oxygen level in the atmosphere. So I always ask them to think about it. The easiest thing is to do a perturbation analysis. So what if we increase the oxygen concentration to 25%? Then we will have like a massive wildfire. After the fire, there will be less vegetation, there will be less photosynthesis, then it will bring down the oxygen concentration. Of course, such process can take a million years, but that's a logic here. But in ancient times, like in the dinosaur age, people expect the oxygen level there is like 28, like 30%, because at that time, the Earth is much more humid. So it's not just the oxygen level, but also the humidity of these vegetations. They control the flammability of the system, Earth system. So about 50 years ago, actually, Andrew Watson and James Lovelock, they look at this problem first time. And I have to say, the experiment they designed is probably the best experiment, combustion experiment ever. Very smart. So very simple. They just put some paper, like put some paper strips into a controlled environment, and they control the oxygen level in that chamber. They also control the paper moisture content, and to find out what's the moisture level and oxygen concentration, you can have the fire. So this is the curve they get. This curve is basically correlating the moisture content and also the oxygen concentration. So if you have increasing high oxygen concentration and even the fuel is wet, you can still have the fire. And using this correlation, you can predict the historical oxygen level on Earth based on the fire carbon footprint. But the question remaining here is the curve they get is based on the flaming fire. What if we consider the smoldering fire? Because we know the smoldering fire is more persistent. It can burn in the case the flaming fire still cannot survive. So it should be the smoldering fire defining the flammability, not flammability, combustibility of the Earth. So this is what we do. We actually did a lot of experiments. We also did massive numerical simulations trying to quantify that curve for smoldering fire. And this is a curve we get. So we found that actually there is additional zone here. So this zone means in this region, there is no flaming fire. There is only smoldering fire here. And it should be this curve defining the combustion limit of the Earth, the fire threshold of the Earth. And with this new curve, we can do a lot of things. For example, we can recalibrate the oxygen concentration on Earth over the last 400 million years, and find out maybe that's related to the evolution of some animals, dinosaurs. That I don't know, but we just provide this threshold for people to reconsider about the oxygen concentration on the Earth's history. So that's something we did before. Okay, about the challenges and the frontiers. I have to say this is very hard. This is the largest fire of us. So I will just cover a few parts. I think it's important. First thing is detection, and the second is suppression. And can we apply some modern technology to do smart firefighting, and also these overwintering fire in the Arctic region, and carbon emission, climate change. So first thing is about detection. So the detection is very hard. So we have satellites, we have airplane, UAVs. These are very good tools. They are very good to monitoring the flaming fires. But for smoldering fires, it's almost impossible because they hide. They hide below the surface. Even you go to the forest, you use like CO sensor to measure it, it's probably you cannot catch it. They are very weak, and you don't know where it is. So this is something very challenging. I don't know. I don't have a good solution yet. Maybe we can have some sensor network of different sensors to measure it, to measure the emissions. One thing we realized is the peat fire generates a lot of ammonia. That's something different from flaming fire. Flaming fire actually generates NOx because the temperature is high. Smoldering, they generate ammonia. Maybe we can use some ammonia sensors to monitor these peat fire, but that's an open question. We still need to explore it. And about the fire suppression, very few research. If you search the literature, it's like less than 10 papers looking into it. It's hard. So from the principle, we know there are 3 ways to stop the fire. Remove the oxygen, it's like smothering. Remove the fuel, and or cooling, quenching it. Removing oxygen, impossible, because you cannot isolate the atmosphere from the ground. Removing the fuel is basically building the fire break that can help control the fire. And cooling, basically you have to rely on the raining rather than the firefighters. You can see, I would say it's quite cruel to send some firefighters to fight these kind of peat fire. They probably won't survive after a few times. So some maybe artificial rain, something we can think of. And also the building the fire break. That's something I just discussed with Nick this morning. Is in Indonesia, actually, the fire service, the forest service, they build this canal. They build this canal on the purpose of help fighting the fire. But it is highly possible when they build the canal, they actually dry this soil. So actually make the soil more flammable, more easy to ignite. So it's quite controversial for sure. If you need to build a canal to help the firefighting, you're actually creating more fires, something like that. So that's something you need to explore. Another issue is, can we monitor these wildfire? Because I'm doing the building fire. We are currently doing the, we call that smart fire digital twin. It's like you have a real fire and we have a digital twin in our computer. So can we use a similar concept to the wildfire? So we have something like satellite, UAV, maybe airplane to monitor it, and we transport the information to the cloud, and we monitor that in the computer. So we can monitor where is the fire or the fire risk real time every day, or according to the historical trend to predicting the possibility of having fire. So this is something has to be done in future. We need a smart system rather than just when the fire occurs, we go there to fight it. We need a more intelligent system for it. The other thing is about the overwintering fire. And this is a new paper published in Nature last year. They actually found this overwintering fire is that the fire actually come up next spring. So they stay in the winter when the temperature is like below 50 degrees Celsius. So this is actually possible, captured by satellite image. And also something related to the permafrost. This is basically frozen soil. And when the global warming becomes stronger, you will have this soil melt and they become very vulnerable to the fire. So that's also something need more research and relate to the also the warming rate in the Arctic region. The one last thing is about the carbon emission. So this loop I have mentioned before is you generate more fire, you generate more carbon, you make everything warmer, and you increase in the probability of ignition and fire. Yes, qualitatively yes, but how strong it is. So that's something we don't know. So every pass, how strong the effect is, and is it like propagating? Is it like enhancing in every pass? That's something we don't know yet. So I think it still was a lot of research in this area, in the global scale. And finally, I want to say this is a very multidisciplinary research topic. And I do the combustion, so I'm an engineer background. So I moved to smoldering during my PhD. And in fact, we found a lot of areas related to the smoldering fire, smoldering combustion. So it's related to the biomass. We are doing using smoldering to remove the bio waste. And of course, related to the wildfire, and it's also related to the ecology. So many things can be done on this area about emissions, land management, and also firefighting. So I think this is a very broad area. A lot of people can get involved, and we definitely need more multidisciplinary research. That's a little summary about what I have shared today. First, the peat fire is probably the largest. I think it's the largest fire. At least it's long-lasting fire on the Earth. It generates about like 10% of global carbon emissions, sometimes a little bit more, sometimes less, and about 3% is from the Arctic fire. And for the peat fire, very easy to ignite, very slow, long-lasting, difficult to suppress. So when I was studying combustion, so my supervisor is famous combustion scientist. He said, so when you think about combustion, if the combustion is very strong, it's usually unstable. If the combustion is very slow, it's probably very stable, and you cannot stop it. So this is exactly what happens to the peat fire. It's weak, but you cannot stop it. So that's a problem. And I think with a small scale experiment and a good model, we can explain a lot of things in the Earth scale. But we definitely need to work more with geoscientists and ecologists. So to do more research in this area. With that, that's the end of my talk. Thank you for your attention.
Thank you very much. It was a great presentation. I learned so much.
Thank you.
Good. I think we have one question online, so let's start with that.
Okay, so someone asked, is there a simple special tool to directly measure the speed of peat fire in the field at Peatland? My answer is no, because the fire not necessarily spreading on the surface. It's very likely spreading below the ground into multiple layers. So it's almost impossible to find out. When you see the fire on the surface, it's like tip of the iceberg. There's even much more area burning below it. So with some like maybe UAV can carry infrared camera to look at the hot spot on the surface, but it's impossible to find what's below it. That's a quick answer.
Yeah.
Thanks, Martha. Thanks, Xinjiang. Thanks, Xinjiang, Jeff Perry. Thanks for a great seminar, very interesting. I've got two questions. I'll ask the first one first, because the second one's, I think, much harder to answer.
Okay.
So your new curve, what's the love curve where you demonstrated smouldering combustion at a much lower moisture content, oxygen level. Yeah, correct. Is it possible to have smouldering combustion without flaming combustion? How does that work out? Or is the flaming combustion under periods of extreme dryness? How does that fit into your sort of theoretical analysis or reinterpretation of the curve?
Okay, so let's say if the oxygen concentration on Earth is like 15%. So basically, I would say at that time, no flame, no tree can burn with a flame. But all these organic soils, all these coals, they can still burn in the form of smoldering. So that's the word I imagine is flame-free but smoldering word.
So the question, thanks for that. I'll take my mask off. So the question is, can you have the smouldering combustion without the flaming combustion, or is the flame, is
ignition
initially the initiation phase? Can you just explore that a little bit more?
Okay, so there are a few types of ignition can happen. First is volcano. That's pretty hot, and it does not need any human intervention. And we also have lightning strikes that just generate ignition spot pretty easily, and they can have self-ignition. So if you have so many peat and very dry, a big area, not raining for a few years, it can self-ignite.
Spontaneous combustion.
Yes.
Okay, great. Thank you. Can I ask the second question while I've got the microphone before I pass it to someone else under the COVID arrangements? So the second, you talked about the firefighting canals.
Yes.
And the importance of those drying the profile. Of course, in 1997, before the El Vivo, there was the Mega Rice project where they built very long, very deep canals across some of the vast peatlands in Kalimantan. Can that event ever be overcome, do you think? You know, in terms of preventing or vastly reducing the peatland fires, or is that just are those fires now a permanent part of that system until the peatlands burn away? That's the question that's much more difficult to answer. Thank you.
You mean how can we deal with it, or you know, just accepting the fact?
Yeah, I'm asking you. Yeah.
Well, it's because I talked to some firefighters from Malaysia. They actually appreciate this canal because when there's a fire, they enter the region. They can just pump to just put the water to stop the fire. But it's really difficult to quantify how much additional fire you caused due to this canal, and actually how much fire you stopped because of the canal. I think it's worth to do some analysis.
Yeah, thank you. It's an interesting topic.
Yes.
But those canals are very large.
Very controversial.
Yeah, thank you.
Thank you.
I think there is another question online, perhaps.
I think it's the same one. Oh, there's another one. What are the medium-term 10 years impact of peat fire on ecological recovery of affected landscape? Can vegetation grow back? Okay, so I'm not an ecologist, but as far from I know, many people have done some research on this area. They measure the pH value of these soils after the peat fire, and many show the result actually quite similar to before the fire. And it's difficult to say because sometimes when you have the peat fire, you kill all these trees. If you kill all these trees, these soils are very easy to lose after rainfall. So you actually not just removing the soil, also removes the vegetations. So it's a combination. So I wouldn't say 10 years is enough. It may change forever. It may change the ecosystem, but I'm not an expert in that area.
Any other question in the room?
Yeah.
Thank you. Yeah, for the online audience, it's Nick Sarowski from UTS. Just interested in detection methods for peat fires. Now, you said that, well, they're underground fires, so maybe not possible to detect, but you mentioned ammonia sensing. I'm just wondering, like, as a method, you know, the combustion characteristics of a peat fire are different from a wildland fire, and they're different from other combustion sources like vehicles. I'm wondering whether you can look in satellite images for areas where you've got anomalously high CO to CO2 ratios, and it's not coupled with a Modus hotspot, for example, and using some method like that to try and detect peat fires.
That's a very hard question. So initially I thought satellite is very powerful and may detect something. But from the small scale experiment, I feel the CO to CO2 ratio, initially I thought it would be very high for smoldering fire. But in fact, in the pyrolysis process, it actually generated even more CO. So the CO to CO2 ratio is even higher. So in many cases, you have a flaming fire, but many of the fuel are not burned. So they release a brown color gas, smoke, hovering around the forest. They probably are pyrolysis gas, so they will have a lot of CO as well. So I don't know if just using CO and CO2 ratio could indicate the existence of the peat fire.
Sure, just like Jeff, I've got a second question. So I think given how much carbon is in play, I guess suppression would be nice. Now, you talked about fire breaks, but in those other 10 papers that you looked at, are there any other options available for suppression of peat fires?
For suppressions, according to the conversation with the fire commanders in Indonesia, is for small fire, they can try to stop it with the water in the canal, but they do develop intuition when it becomes too large. They just run away because there's no way they can handle it. Just wait for the rain season to come. It's beyond human capability. Yeah, there's another 2 questions. So what type of challenge do you face or foresee in doing such a complex multidisciplinary research, interacting with engineers, ecologists, firefighters, and others? It's very hard. So I know the ecologists, they think very differently, and I'm an engineer, so sometimes ecologists treat us as like technician. So sometimes the way thinking is different, and the firefighters, they have their own missions. So they just want some applied research they can solve their problems. So it's very difficult to bridging that gap. It's challenging, but I think go to the conference, talking to everyone, go to different community, you have some idea about what other people think, and that helps. Yes. Like doing village. And second question is, can we determine what a smoldering fire on the peat soil has been extinguished? What indicator, examples of temperature? That's not possible, in my opinion. I showed like a fire burning for 10 days in our lab. And the reason we feel it's extinguished is because our thermocouple sensor is not touching the burning area. That's for just such a small sample. And for this temperature measurement, it's like point measurement. You cannot locate exactly where it is burned. And on the surface, it's just pretty cold. You don't feel the heat beneath it. So I would say very hot, very hot.
I got a question.
Okay.
So you mentioned that the oxygen and the soil moisture content is a determinant of the probability of emission. But I guess that as the peat fire is progressing, the soil moisture also changes. How is that interaction, and would that be a potential area to explore detection using soil moisture changes?
So when I say the moisture content is, of course, when the fire spreading to it, it will dry it out. That's the requirement to keep the fire going. So that's not something that's already part of the system. So if the peat is very wet, the burner region cannot spread to the unburned, so it will stop automatically. That's where we found that limit. So, but in reality, of course, the moisture distribution is not homogeneous. So that's actually the reason I showed the photo before. You see these very weird patterns because the fire actually follows the dry areas. They skip the wet regions. So you see these very fingering patterns.
All good. Yeah. Well, join me to thank again Sijan for his talk, and yeah, I hope you were enjoying Canberra.
Thank you.
Thank you.